Hi, I'm going to talk about 3x3 transformation matrices. Matrices are a way to define a coordinate system or a subspace within our own main space, the world space. So in the world space, we already talked about the I hat, j hat, and k hat vectors, which are the standard basis unit vectors. They are the components by which we build up our position. So for example, let's say here I have this position P, 2, 3, 4. I arrive to this position by stacking up scaled versions of my standard basis unit vectors, and this will get me here. So as an example, let's say 2, 3, 4. So basically I'm going to multiply I hat by 2. I'm going to scale I hat by 2. And so this will give me this X vector component 2, 0, 0. I'm going to scale J hat by 3. And this will give me this y vector component 0, 3, 0. And I'm going to scale k hat by 4, which will give me this z vector component 0, 0, 4. And these added together here let me arrive to this position. Now, these are a fixed reference, and we need, of course, a fixed reference so we can judge everything else through it. But what if instead of using this standard basis, I use another basis? Let's say that I use a different set of 3 vectors so that I build up my positions in the same fashion that I've done here. And so as I change those vectors, the position also is going to be changed. So this is what transformation matrices are going to do. So here in Lightwave, we don't have a dedicated data type for matrices. What we have is their components, explicit components, right, up, and forward. Right is associated with X, up is associated with the Y-axis, and forward is associated with the Z-axis. And so together, they will be used in the same fashion as the standard basis unit vectors to build up position. They're called 3x3 because if I put their information, their data stacked up together, it gets like this, a 3x3 array of scalar values. It's called this identity, this matrix here is called identity because if I try to transform any vector by it, I basically am going to get the vector itself. Just like, for example, 1 is the identity of multiplication because you get the value itself, or 0 is the identity of addition because you get the value itself. So this matrix here is basically not going to do anything. And if you notice, there's some 1s here on the diagonal, and it basically matches the values for right, up, and forward match the values of I hat, j hat, and k hat. But of course, as we deviate from these values, as we go away from them, we're going to see differences in the positions. We're going to transform the positions that are built up with these basis vectors instead of these basis vectors. So let's look into that here in layout. I have this position P, and it's object that's null that is being tracked by a vector. And I have these other vectors, the right, the up, and the forward. And these 3 form a matrix. And they have a common parent, this yellow box here. And let's say that I rotate that yellow box, and you can see I have a magenta vector showing up. But I can transform, basically the magenta vector is this position P being transformed. And I can transform it like, a regular 3D transformation. I can rotate the box, I can scale it, and you can see the position is being scaled. Right, so this looks very common, like we've seen with the transform 3D. The difference here is that I can also skew something that I couldn't do before. So by doing this, I'm skewing the space in which this position is being described. And so this is something that we haven't seen before. Now, what is the magenta vector really? What is the transformation that is going on in here? And so what's going on in here is that this position here is the same as this. So this one has 0.5, 2, and 3. And this position is still 0.5, 2, and 3. It's just that description is not being used in the world space, the I hat, j hat, and k hat matrix, but within this matrix, within the space defined by these vectors. So relative to these vectors, the matrix defined by these vectors, this vector here is the same as this vector here. It's just that for the world space, of course, they're going to have a different output. So let's look into the components and the axis so that becomes maybe even more obvious. So I'm going to switch on the components and axis switches here. And as you can see, for example, if I grab this yellow object, if I scale this, you can see the axis changing. So basically what I'm doing is I'm not exactly changing the position directly. What I'm doing is changing the components that build up this position. I'm changing the space where this position is being built on. So these are a fixed reference, but by having another triplet of vectors that I can manipulate as I'm manipulating here, I can have the position, the description of the position arrive at a different location. So I have this vector here that it still is 2, 3, 4. It's just that since the building blocks are different, the end result is also going to be different. Right, so you can see, for example, as I scale, let's say I push this out, the component, the X component is still half of my basis. Or let's say that here I have this basis being, the up vector being like this, and the Y component is basically 2 times my basis up vector. But if I skew it, the component also gets skewed. And if I stretch it up, the component also stretches up. And so this is why, even though the coordinates of this vector are the same as this one, I end up with something completely different in the world space. So let me reset all this because it's getting messy, and let's go into another object. Set this. Let's see. So I'm going to turn this off, and I'm going to switch to another object. Have this little cube here, and I'm going into its displacement node editor. So edit nodes, and here basically what I'm going to look at is the proceedings that are required. How can we transform a position with a matrix and with the nodes? And so there's 3 ways that I've laid that out in here, and they are all transforming the same position vectors, the world spot, so the point positions of this mesh by this 3x3 matrix. And if I open up this compound, you can see that there's 3 sources for matrix data. I have the first one is these arrows here, and that's what I'm going to look into first. And then I have explicit parameters, transformations that can be done by a 3x3 matrix. And then the last thing I'm going to look at is an object, so an item info that has right, up, and forward, and I can use that to mimic another object. So first, let's go to the arrows and check the ways in which we can transform a vector by a matrix. So this one is the most verbose one. Is basically describing in nodes what I've explained here about scaling the basis vectors, the ones that we are to use to build up our positions, and then adding them up together. So here I'm using the matrix components, and I'm scaling each of them by the respective scalar component of the position that I want to transform. And then the result of all those scaling operations is added together, and this will result in the transformation of my position. So let's look into that. And so if you can see, I get the expected result of this. Here I'm having a skewed matrix, or I can just grab, let's say I can grab that yellow box, and I can just rotate the 3 at a time and scale them, etc. Can have this type of transformation. Right, so let me oppose this so we can see that the result is the same for all 3 implementations. The second implementation that I have here is one that uses the transform to node, a native node, to make a matrix transformation. The only annoying requirement is that I transpose the matrix that I'm going to use. So this one I don't like much because it forces me to transpose the matrix. What is to transpose the matrix? Well, to transpose the matrix is basically to convert rows into columns and columns into rows. So you'll see here that the right vector is 1, 2, 3. But where you see this configuration here? Well, you see it has a column here. And you'll notice that we have this column of values here, 1, 4, 7, and the right vector becomes 1, 4, 7. So row becomes column, column becomes row. The only values that are maintained are the ones in this diagonal. All the other ones jump across that line. So the values that you see here with the same color, they basically swap position with each other. And so this is what it is to transpose a matrix. So I have this requirement with this one, and I don't like it that much. So what I end up using is the transform node by Akira Azaki. And it's very simple. I just plug in the components of the matrix that I want to use and the vector that I want to transform. And then by plugging that in here, you can see that I get the same exact result. So all these 3 will do the same thing, as you can see, as I plug them, and nothing changes. But this one is definitely the most simple one. You only have to be careful because at times plugging some input directly onto the transform node, it's going to produce errors. And so sometimes having this pass node is a requirement to avoid any errors. Anyways, this kind of shows how these arrows can, this explicit, matrix data can transform the point positions. Let's look into something else, another source. And so let's look into these 3x3 matrix parameters. This is just a demo compound that I just I'm just using to show explicitly the transformations that are possible with a 3x3 matrix. So I have here the same similar list. So from the direction and the length of the components of the matrix, we infer transformations like scaling, reflection, rotation, and the one that is sort of new to us, that is shearing. So let's look into the first input. We have here scaling, and just like the transform 3D, you can scale the positions on the axis. We also have reflection, so I'm gonna skip shearing for now. And so we also have reflection. Let's say that I want to reflect my mesh on the x-axis. I put one in here, and now you can see that the polygons are flipped, but the positions are also flipped. So the bright red polygons are on this side instead of being on this side. And so I can flip multiple axes. So now I flip the z-axis as well, etc. And I can rotate my mesh, just like in the Transform 3D. Right? The only new addition here is the shearing. And so what is to shear? Well, when I say shear XY, it means that I'm going to shear, I'm going to move the positions on a plane. So the plane that is perpendicular to the x-axis. So this is the x-axis of this object in particular, not the world x-axis. The x-axis, the right direction is around here. And so I'm going to move perpendicular to that plane. So this plane here. And I'm going to move on the y direction. So if I come here and I scrub this, you can see that it's moving perpendicular to this plane on the y direction. And so the mesh can get really skewed by this. And let's just look at another one, shear ZX. So it's going to shear on the Z plane. So this plane here, and it's going to move on the X direction. So this direction here. It's going to look at that. If I come here and do this, does something like this. You can see it's moving on the X direction of the object, and on the plane, on the Z plane. Okay, so the ability to shear. Of course, I don't use this compound or explicit parameters like this to change the mesh. You can use it. I just use this for as a demo. But the ability to shear an object, to shear some positions, is very nice because it allows me to be able to copy, to mimic any pose in the scene. Let's look at that with the item info. Just a note, I'm using the direction nodes in here just because it's easier to scrub values in here. Sometimes with the vector, having something like 0 and scrubbing this up to 1, it can seem like it takes forever, and it's much easier with these ones. That's the only reason I'm using the direction constant node in here. There's no other reason. So let me disconnect this, and let's say that I have this object here, this parent and this child. And so let's say that I rotate the child like so, and I even scale it like so, and I scale the parent as well. So I'm gonna scale the parent like this. Okay, so this is something that it's not, I cannot easily copy or mimic the pose of this object. Let me reset that and just rotate it a little bit on this axis. Okay, so the pose that this object has is not easy, or I cannot mimic it by just having the transform 3D with scale, rotate, and translate. I cannot get these skewed matrix that you can see here, where the x-axis and the y-axis don't do 90 degrees anymore. I can only do that by using matrix. And so let's look into the item info to perform this sort of transformation. So the item info, right, up, and forward, give me the orientation of an item relative to the world space. And of course, the context, or the position, the base where the tail of the vectors start from, is the item world position. So this is the position that this item has relatively to the world space. And this item, of course, has its parents. It has its parent A, parent B between it and the world. But the right, up, and forward outputs allow me to have the full evaluation of the whole hierarchy from the item to the world, and what's the resulting pose in the world that the item gets by its own motion or by the motion of the parents. Unlike, for example, position, rotation, and scaling, which are the motion channels of the item alone and are relative to the first parent in the hierarchy. So this means that with right up and forward, I can easily relate items in the world space because I have access to how they look and how are they posed in the world space. So let's look at that. And I have here this my object, my cube, and we're gonna plug here this object item child, this item in here. I'm gonna plug its right, its up, and it's forward. And you can see that it mimics the orientation, the scaling, and the skewness of this child item correctly. To show my point about the limitations of the transform 3D, you can see that I have here this conversion from matrix to scale and rotation. I'm going to talk about it next. But if I plug here the result of that in here, you can see that I do not get a skew pose like this item has. I have basically some perpendicular axis, and so I cannot reproduce with just the transform 3D what's happening to this object throughout the whole hierarchy. So this is something that matrices are very useful for, to basically get the final pose of an object in the scene. And the same, I was not going to talk about matrix inversion, but I think I can just address it here quickly. And so the same way I can mimic an object correctly from its pose in the 3D scene, it also means that I can remove, I can take out the influence of some object transformation in the 3D scene, including the object itself. So let's say that I pose my cube here, and I'm going to pose it. Let's say I'm going to rotate it, I'm going to scale it, and I'm gonna have this this ring here that's its parent. I'm gonna rotate the parent as well. Let's say I'm gonna orient this like so it gets a little bit skewed. Okay, and I'm gonna scale the parent down. Okay, so this is a transformation that is quite drastic. And let's say that I want to revert this. I want to take out the transformations that this object went under by its own motion and the motion of the parents. I can do that by inverting the object own matrix. So let's look into that. I'm going to put a copy of this in here, and I'm going to select the round cube matrix object, which is the name of this object, and I'm going to call the invert node. Matrix invert, and I'm going to connect right up and forward in the appropriate ports, and I'm going to connect them in here. And so what will be the result of this? So my object is posed, the parent of my object is posed, and so the points of the mesh are transformed by the pose of both the object itself and the items in the hierarchy, up in the hierarchy. So by transforming the positions of my mesh by the inverse matrix of the object, what I get is that it seems that nothing happened to the object. And so you can see that as I rotate, you can see the bounding box change because the object is actually changing. So this is, the object is going under an actual transformation. But as the displacement solves the inverse matrix of the object itself, it kind of looks like nothing was done to it. And even if I change the parent or I scale it, you can see that nothing happens. There's only one limitation, is that when you go into negative values of scaling, the polygons flip, but the positions remain in the same place. It's a limitation of the displacement node editor, unfortunately. But you can see that it seems that nothing happens to the object, and it's a bit strange. Why? Well, so with this, I'm able to counteract if we say that the resolution of the item and the parent objects, the right up and forward matrix transforms the vertices. So I can go backwards. So this will make, as we've seen, like I copied this pose. So if a matrix allows me to copy a pose, so I have some positions and I'm able to copy a pose. If I have a pose already, what do I need to do to have my positions like they are not changed at all? Well, I go with the inverse matrix. And so transforming some positions by a matrix or by the inverse matrix will be crucial, so we can navigate between spaces that are defined between different objects. So different objects have different poses, and those poses define different spaces. And so by transforming positions by matrices or their inverse, this allows me to go between objects poses or object spaces.